This is a February, March 2022, variant 42 question. Question number 2. Fixed mass of gas of an ideal gas has a volume V and a pressure P. The gas undergoes a cycle of changes, X to Y, then Y to Z, and Z back to X, as shown in figure 2.1. Table 2.1 shows data for the pressure, the volume, and the temperature of the gas at points X, Y, and Z. X, Y, and Z. These are the values in the table. Then in part A, state the change in internal energy delta U for one complete cycle X, Y, Z, and X. To do this question, we need to know that when the gas makes one complete cycle, in this case, X to Y, then to Z, then back to X, the change in internal energy is 0. This is because we start from X and returns to X. There's no change in temperature when the gas returns to X. For an ideal gas, the internal energy is equal to the sum of the random kinetic energy. The random potential energy is 0. And the random kinetic energy is proportional to temperature. And since there's no change in temperature, there's also no change in internal energy. So to get the 1 mark here, the answer is delta U equals to 0 joule. The reason is because there's no change in temperature when the gas returns to X. Then in part B, calculate the quantity of gas in moles. We will use the pressure, the volume, and the temperature for the gas at X to calculate N. This question carries 2 marks. The first mark is for PV equals to nRT, N equals to PV over RT. We will substitute the pressure, the volume, and the temperature of the gas at X into the equation to get N equals to 0.14 mole, which carries the second mark. Then we need to fill up the table. 3 values need to be filled up here. This value, the pressure at Y, the volume at Y, and the volume at Z. We know that the pressure at X is 1.5 times 10 to the power of 5 Pascal. And then the volume at X is equals to 4.2 times 10 minus 3 meter cube. We know that the pressure at X and Y are the same because of this horizontal line. So therefore, the pressure at your Y must also be 1.5. So this is 1.5. But we do not know the volume at Y. We do not know this volume. We also know the pressure at Z is 5.1 times 10 power 5 Pascal. But we do not know the volume at Z. But we know that the volume at Z is the same as volume at Y because of this particular horizontal vertical line here. The volume at Z, same as the volume at Y. In order to calculate the volume at Z, we can use 2 methods. The first method is to use PV equals nRT. Your N equals 0.14 because the question says that there's a fixed mass of an ideal gas, fixed mass. That means the quantity of gas is the same, so which is 0.14 moles. At your Z, the temperature is 782 Kelvin, and then the pressure is 5.1 times 10 power 5 Pascal. Substituting the values of N, temperature, and pressure into the equation will give you 1.8 times 10 minus 3 meter cube. That means the pressure at your Z will be 1.8 times 10 power minus 3 meter cube. And since the pressure, and since the volume at your Z, same as volume at Y, this also be 1.8 times 10 minus 3 meter cube. Another way to calculate the volume at your Z is to use PV equals nRT. But this time we rearrange the formula. PV over T was NR. NR is a constant because N and R are constant. Therefore, your PV over T is a constant. So you can say that the PV over T at X is the same as the PV over T at your Z. So it's substituting the values into the equation will give you VZ equals to 1.8 times 10 minus 3. So with this, we give you this answer, 1.8 times 10 minus 3 meter cube. And since we know the volume at Z, we also know the volume at Y. which is 1.8 times 10 minus 3. In part C, with complete table 2.1, use a space below for any working. The missing value P is 1.5 times 10 minus 5 Pascal, which will carry 1 mark. And then both the missing volume, which is 1.8 times 10 minus 3 meter cube, will carry the other mark. We need to calculate the missing volume either by using PV and RT or P1 V1 over T1 equals to P2 V2 over T2 as discussed in the previous page. Then for D part 1, the first law of thermodynamics for a system may be represented by the equation delta U equals to Q plus W. This question carries 3 marks. We need to explain what your delta U, your Q, and your W represent. Each of these will carry 1 mark. So your delta U is the increase in internal energy of the system, 1 mark. Then your Q is the thermal energy supplied to the system, which is a 2nd mark. And then your W is the work done on the system, will carry the 3rd and final mark. Then for part 2, explain how the first law of thermodynamics applies to the change from Z to X. To do this question, we need to know that the volume increases from 1.8 times 10 minus 3 meter cube at Z to 4.2 times 10 minus 3 meter cube at your X. That means the gas expands and work is done by the gas. The other thing you need to mention is that the temperature of the gas decreases from 782 Kelvin at Z to 540 Kelvin at your X. The decrease in temperature shows that the internal energy decreases, since the internal energy of an ideal gas is only due to the random distribution of kinetic energies. The potential energy is 0, and the kinetic energy is proportional to temperature. And since the temperature decreases, the internal energy decreases. So to get the 2 marks in this question, first mark is to mention about volume. The volume increases and the work is done by the gas. The second mark is on the temperature. The temperature decreases and therefore the internal energy decreases. And this is a summary of the facts that you must know to solve this question. You must be able to use PV equals nRT to calculate your N. Then you must be able to recall and use the first law of thermodynamics, which is delta U equals to Q plus W. You must know what your U, your Q, and your W represent. And when is your U, your Q, and your W positive or negative? Then number 3, relate a rise in temperature of an ideal gas to an increase in its internal energy. This statement only applies to ideal gas, because for ideal gas, the internal energy is due to the random distribution of kinetic energy. The potential energy is 0.